So in previous lecture, we had just introduced the concept of kernel, how from our dual problem, how we use the kernels to separate our non-linear separable data by simple linear separable, simply using SVM. We are just simple discuss about the primary concept of kernel. So in this lecture, we will discuss about the specific kind of kernel that we call polynomial kernel. Okay, simple, it is the polynomial kind of kernel. Suppose let's take our kernel. We have taken our kernel is like that, x1 and x2. Suppose we have a two data points, that is x1 and x2, or simply you can call, if you have two vectors x1 and x2, as you can call is x1 and x2 as vector, or you can call it is a simply it is a data point. Okay. Suppose our polynomial kernel would be look like this, that is x1 transpose x2 plus c into t. Okay, we will see x1 and just if you remember our dual problem, there we have see that we are simple using x1 and x1 transpose xi transpose xj. Okay, simple, if you just it's compare to our cosine similarity, if the norm of this vector is equals to 1, then it will, if you simple this term, it will be simply one kind of cosine similarity. And instead of simple cosine similarity, we have simple, if we just take in a simple any kind of similarity functions, and instead of any kind of similarity function, if we there use the kernel functions, then I think this terminology will work better for also non-linear separable data. Okay, and also if you just remember logistic regressions, in logistic regressions chapter we already seen that for a non linear separable data, there we are using, they are simple, we are using the for a non-linear separable data features transformations or simply features engineering. And these features transformations and kernel trick are both are the same kind of things, just we are visualize this thing into different angles. Okay, so simple. First take, if you just see this kind of data, this kind of data, see in logistic regressions for a non-separable data, non-linear separable data, we see this kind of data in linear regression. Just I am rewrote this picture again. Okay, suppose this is one kind of data sense, and let's take this is our another kind of data set. So simple, if you see here, simple, no hyperplane can separate this data. Okay, no hyper can, it is impossible for no hyperplane to separate this kind of data. Okay, so in such cases, if you just remember logistic regressions, suppose if we, for this data point, if we have two features, let's take, if we have two features, that is f1 and f2, if we have two features, then in logistic regressions we see that the features 1 and features 2, these two features, we are transform these two features in f1 square and f2 square, these two space. Okay, simple, we are transform the f1 and f2 into f1 square into f2 square, simple, by using our features transformations or feature engineering. Okay, and this thing we will done, if you see this thing we will done explicitly we will done this kind. Simply by using explicitly we can use it. The same kind of thing we are doing in the polynomial as a kernel trick also, but this thing we will do internally, means not explicitly, we are doing it implicitly. Okay, implicitly, just we are seeing this kind of thing in logistic regression. Okay, this thing we are seeing in logistic. Now simple, here I am as an example, just take first an example. I think instead of using first going to the general case, if we just discuss the general case through an example, then it will be better for us. Okay, just first taken our d quadratic term. It is simple, a general term, general polynomial term. Just I am taking here a quadratic term. Okay, let's take a quadratic term. Let x1 x2 is equals to x1 transpose x2 plus c. See, instead of c I am just using here 1, and instead of d here we are using 2, because we are taking here the quadratic kernel. Okay, simple, this is our quadratic kernel. This is simple, our quadratic kernel. Okay, now let's take our set of data points, this set data points in two dimensional. Simple, just for simplicity I am just taking the our data point is in two dimensional, belongs to two dimensional space. So here x1 and x2 will be lies in 2D space. Okay, let's take it is lies in 2D space. So if x1 and x2 lies in 2D space, then what will be the form of x1? That is x11, x12. Okay, this term will be x21, x22. Okay, for simple set, let's take our data point lies in 2D. Now we are simple, just we are simple putting this form here. So now our kernel will be here. So first see the multiplications of these two ones. So just I'm first going to multiply these two, one x1 transpose x2 means what, x1 transpose will be this like x11, just I'm just simple. If it is a column vector, in general case our data point is always lies in column vector, so our x1 transpose will be like this, and x2 will be a column vector. Okay, so x11 into x21, just multiply this term plus what, x12 into x22. Okay, just I am putting, instead of here I am putting this term. So just first just rewrite this equation. One second. So now our kernel equations will be converted to a of x1 x2 is equals to, just I am first writing 1, then I am introduce this. Okay, now just simple, just I am going to simplify this thing. So simply here I am using this formula. If you forget, just I am writing here a1 plus a plus b plus c whole square is equals to a square plus b square plus c square plus 2ab plus 2bc, 2ab plus 2bc simply plus 2ca plus what, okay, I think 2ab. Okay, I think this is okay. Okay, just I am inputting this formula here. So now what will be our now equations converted to square x11 square x21 square b square plus c square means x12 square x22 square plus 2ab 2x11 x21 plus 2, suppose I am first taking 2ca, I am first taking this term plus 2ca means x12 x22 plus 2bc this term plus 2x11 x21 x12 x22. Okay, So just now I'm going to just simplify same thing. I'm just going to simplify this. If I again simplify these things, just I am just going to factorization in such a way that we are here, this term we will going to factorize. So what will be the factorization term? So just see. So 1 into 1 multiplication is 1. Just first time 1. So here just we have seen there, here it is the square term, and also here it is a square term. So simple, here I am just a single first. Here how much term? 1 2 3 4 5 6. So 1 2 3 4 5 6 into this one. What's this term? The first one here will be first one. So I am just here writing x11 x21 plus also here x11 x21. So both term multiplications will be here. Simply here now I'm just writing here x12 x22 plus also here it will be x12 x22. Now coming to here, I am just first write the a root 2 means root plus root 2 is equals to root 2. I think it is no problem. Now we have to just say, just we have taken the root over root term, just square root term here we have to take. Sorry for that. I am here taking the plus signs. Not, it will be not here plus sign, it will be the comma instead of plus signs. It will be, because we are going to multiply, we are just simple going to multiply these two things. Okay, just its transformation plus this term. Simply it is a multi dot product. Simple, just it is just, don't be confused about that. It is simply a dot product. I think it is simply a dot product. Comma, comma, just comma. So root 2, simply it is, I think if we can do one thing also here. Instead of taking root 2, if I just consider simply this term and this term, it will be better for us. So just again re-simplify this thing. I think it will be easier most. It is one way, but on this way, so this simplifications is more better. Okay, just stop it. This, just remove this. Just I am here taking this for this one. So first I am taking 1, then instead of root over I am taking this term one vector and this term in another vector. Suppose first it will be comma instead of x11 square, first one x12 square, second one, then it will be root 2 x11, then this term root 2 x12, then this term x11 x12. Just means our main motto is we are just in one vector we are just taking x1 vector. So just read the x1 means what vector? x11 and x12 means all the components of x1 we are just trying to write in one vector, and x2 vector just x2, if you see x2 1 and 2 2, and in another vector we are just writing another components of x2. So for just this is our main motto. Okay, so x12 plus root 2 into x11 x12. Okay, in simple dot product of this one 1 plus x21 whole square, x22 whole square, it will be root over, sorry I am again written here plus sign, sorry for that, sorry for again, just it will be simple comma x22, okay, root 2 into x21 root 2 into x22 and root 2 into x21 22. Okay, it is simply a dot product, simple dot product. Just I think you have understand the simplifications or form to this vector. Just if you recall this vector, if you just recall this vector as x1 dash, and if you just recall this vector x2 dash, simple, we recall this vector x1 dash and recall 1 dash. So now if you just see our this vector is which dimension, this vector is lies on x here, this vector, this just see this vector using this vector simple, this vector lies on x1 x2 space, x1 and x2 space, and this vector, just this thing is lying on in which vector. Suppose if we just simple, I am again rewrite x dash transpose 2. Okay, here we have simple x1 if this vector is lying on x1 x1 x2 space, and simple this vector is lying on this lies on x1 dash x2 dash space, but both are the same thing. We are just visualize the thing in two different dimensions, but actually these both are the same thing. Okay, just I think you all over understand it, how we convert our x1 x2 space to our x1 dash space to x2 dash space. If you just see one thing, visualize it, these dimensions, this dimension is for what, 2D dimension, but if you see x1 and x2, if you just see our x1 dash and x2 dash is in d-dimensional space, x1 and x2 two-dimensional space, but x1 and x2 is 2D dimension, and x1 x2 is in 2D. So by using simple kernelization, simple kernel trick, simple simplifications, we convert our data points from 2D to 60. Okay, now we will see in 60 space this data is easily separable. Okay, just I am discuss this thing, I am just summarize this thing in finally I am going to summarize. Here we are simply by we have two data points x1 x2. Just if you just compare this thing, yeah, here we have suppose we have here our data points. If you just compare, we're just going to compare this thing x1 and x2. So in simple, in your logistic regression, simple using the features transformations, we are converting our x1s and x1 and x2. So using simple features transformation, we are converting this transformation x1 square and into x2 square in logistic regressions, in simply using features transformations, and in polynomial kernel you see that we are simple converted our x1 and x2 by simply one kind of x1 is x1 square, because here included x1 square. Okay, simple, this kind of functions we are using here also, but it is we are using directly, that is explicitly, but here we can simply use this thing in implicitly. Okay, just write this thing. Here we are converting x1 dash and x2 to x2 dash. Okay, here simple we are using features transformations. Here we have this one is 2D, this thing is 60. For logistic regressions, we are simply transform this thing by using simple features transformation or features engineering, but in a polynomial kernel, but in our SVM, here we are simply using what, polynomial kernel. example in SVM we are using polynomial kernel to transform this. Okay, and we are see that we will see that in this page our data set is x1 transpose x2. Now it is a simple using polynomial kernel. Here we got our data set x1 dash transpose x2 dash. Okay, in a actually in is just if you just compare these two things, polynomial kernelization trick and just logistic regressions thing. In kernelizations and the features transformation in logistic regressions, both the things are the same kind of thing. One in logistic regressions we are doing the same thing in just explicit way, but in SVM we just doing the same thing in implicit way. Okay, so just write down this thing: kernelization. Okay, if we add d dimensions features, then by simply in logistic regressions, by simply using the features transformations, we are converting this thing in d dash dimension. And how we do that? In internally we are doing this thing. Here simply we are here using in SVM, here simply we using this, just this different color here. Here in SVM, here we are using the kernel trick, and here we are simply we are doing internally, or we are just implicitly. And here how it is doing, and simply here it is doing in explicitly. Okay, in logistic regressions we are doing this thing explicitly, and in SVM we are doing this thing implicitly, but both are the same kind of thing. Okay, here just you see here our data set is from transform x1 dash to just f1 to f1 square as well. Here also we are transforming this thing x1, just compare this thing x1 square x1 x square, but rest of the sum, because here we have constant simply polynomial. Okay, I think till now all the concept, everything is clear. Now just want to add one thing. If you are not, if you are just you're not interested, then you can close this video. Otherwise, if you're interested, please you can listen. So in mathematics there have one theorem. It is called a Mercer's theorem. In mathematics, if you are a mathematics student, if you are just if you are interested to learn this theorem, if you just Google search Mercer's theorem. Mercer's theorem. If you just Google search it, in Mercer's theorem, they will say the same thing, simply using the kernel trick. If we just simply using kernel trick, that what I am doing till now, this theorem is actually in mathematics. This theorem is telling the same thing. Okay, if you simply using kernel trick, then we can easily convert one dimensional to another dimension. Easily convert something. And one thing here, our d, in typically our dimensions of the d dash will always greater than dimension of the d. In the we see in this here, our in x1 x2 is lie in 2d, but after transformation we see that the x1 dash and x2 dash lies in 6d. Okay, the same thing is called in Mercer's theorem. Okay, we are simply, if we transform using kernel trick d dash to d to d dash, then our dimension is, in typically, not always, in typical there in always there have some exceptional case, but in typically it is our just transform dimension is greater than our previous dimension. Okay, here. And one thing, in this space our data is non-linearly separable, but one thing, in this space our data is linearly separable. Okay, so this is simple, the Mercer's theorem. Mercer's theorem says that means there have also is some mathematical conditions in Mercer's theorem. There has some mathematical conditions, I am not discuss about these conditions. So if you are interested, then Google search it, you can easily find from Wikipedia, and there have many research paper on Mercer's theorem. Okay, just some main thing of Mercer's theorem is that the dimension is always in typically this dimension is increased. For some exceptional cases, this theorem will not work, but in typically this our dimension is most of the time increased. Okay, I think this polynomial kernel all about clear. Just I am taking a simple quadratic kernel example. If you are interested, there have many problems. Okay, and also in description box I am sharing the some exercise about the polynomial kernel. If you are interested, then you can go from there. So I think this lecture is all about clear. If you have problem, please comment below. Okay, thank you.